Do this, go back, do this. Every single step is completely orchestrated by you, the programmer. And the computer blindly follows it, much like a train going along tracks. It can't go anywhere. It's going to go exactly as it is. Okay, if a region of the tracks have collapsed, that's it, the train's going to go over. Okay, it's completely one-dimensional, like a train. So one idea is to build a self-aware system to make programming a lot easier. So here's the idea. So let's say at the bottom I show you a computer with a bunch of cores and I/O devices and so on. And at the top are a bunch of applications. Okay? And today the applications tell the computer, do this, do this, do this. Instead, what I do is I have the application convey its goals. Okay? Let's say I have a video application. Okay? As a video application, I convey the goal to the computer saying, I need to be at 30 frames per second. Okay, so the computer and the system knows that the user wants 30 frames per second, and the operating system is going to help me. So application 2 conveys its goals, and what we do is we embed something called a heartbeat inside applications. Okay, it's a new interface. So users can say heartbeat, and that causes a system level event. This one here is an old style way of writing the program. If you pick it off the web, this is what it will do. So you'll see a picture of a tractor moving along. The video has been encoded. And on the left-hand side, you see the application heart rate. And the right-hand side, you see the number of cores. The application writer has written this for one core. And this is what the video looks like. It's very jerky. But the heart rate is only 6. Remember, to get good quality video, I need 30 frames per second. And the user knows this. Okay, user has no control on this beast, the computer. And the computer says, okay, I give you 6. Take it or leave it. Okay, that's today's approach. So there's an alternative to this. And that's a self-aware system. So under this prototype operating system that MIT is putting together, this is a self-aware system. And the video encoder tells the system, I want to achieve a heart rate of 30 frames per second. Okay? And what the operating system is doing is it's looking at the heart rate. If the heart rate falls below 30, the operating system gives the application more cores. Here, take a couple more cores. Okay? If the application is still below 30, it gives it more cores. And the application is written to be able to take advantage of more or less cores. If the heart rate goes above 33 or 34, the operating system will take away cores from the application. Okay, just imagine if in your car, you want to go at a given speed. You govern the speed of your car by pressing on the accelerator. However, if you have this thing called cruise control, you set cruise control, and you can see the car is completely managing itself. Think of this as cruise control for applications. So just see how it works. So heart rate is 13. The system has 2 cores right now. So 13 is way below 30. So notice, the operating system gave the application 1 more core, 2 more cores, rapidly brought it up to 6. And you saw that the application went up to 30 frames per second. Now, the heart rate is going up, so cores will be taken away. So notice I've gone down to 4 cores. And the reason is that in the video, as I was looking at a large piece of video, things were not moving as fast, and so I could do it much more much more effectively. I'll show this again very quickly. So I start with 2 cores. It's still, the video is jerky. The system says, okay, take 3, take 5, take 6. Heart rate's gone up to 33, and the video is much, much better looking now. So I'm still taking 5 to 6 cores. And now as I'm panning and going further and further away, I don't need as much computing because things are mostly stable and I can take away cores from the system. But the heart rate is still at 30. Just a simple idea. Not only can this help programmers make programming easier, I can use any goals that I want. I can have a goal that says, give me the lowest energy. So I can match many different kinds of goals. So finally, to conclude, just to reiterate, a big disruption is happening as we speak. The many-core cloud disruption. These are disruptive technologies, but many challenges exist. We talked about 3 challenges. The interconnect challenge. We can overcome that by going to mesh architectures. There's the operating system challenge. We can build newer operating systems. What's after Linux and Windows? We need the next big thing. The third big frontier is to manage complexity, to make systems easy for programmers and users to deal with. One possible direction is self-aware computation, where the systems can think for themselves, rather than my having to tell it every little thing. But most importantly, rather than dwelling on the challenges, we have a lot of opportunity. As I said, disruption breeds opportunity through innovation. So my question for all of us is, are we ready to capitalize on this big disruption? Thank you.
Well, thank you, Professor Agarwal. May I now request Mr. Ponton to present a memento to Professor as a token of our appreciation.
Thank you. Which says all you've talked about is increasing number of cores that increases processing. What about applications that care about I/O, memory, and so on? So in this talk, I talked about processors and interconnect. What the interconnect lets you do is allows cores to talk to each other. So now if cores have to communicate, you can do that. You need I/O. And so multi-cores need to worry about I/O. So in this chip that I talked about earlier, notice that with a mesh network, as I increase the number of cores, I get more and more perimeter available to me. So I can use that perimeter to put more and more I/O devices. So this chip with 64 cores does not have 1 memory controller, not 2, but 4 memory controllers. It needs more memory bandwidth. I/O, the graphics processing units, GPUs from places like AMD and NVIDIA and a bunch of others. They're also coming out with many cores. But so far, their focus has been, initially was on graphics, and they found that they can extend the architecture to support slightly more general computations. So here I focused largely on processors that can run Linux. They're general. But to my knowledge, I don't believe the NVIDIA processors run general operating systems and so on. So the use has been limited to... Second question is actually a very, very hard question. What do we do about power? It's a very hard question. And as you might imagine, there's a lot of research going on to increase the power efficiency as we get to 1,000 cores. Just as an example, in an existing Intel core, in an Intel quad core, each core consumes on the order of 20-25 watts of power, each core. So if I just take that architecture and put 1,000 cores down, that's 25 kilowatts of power. Imagine a computer, your desktop, 1 kilowatt. Think of an electric iron, your press, as 1 kilowatt. Imagine 25 of them on your lap, okay, or in your server. It doesn't work. So we have to do something else. This kind of architecture. So the key idea, I think the key, I give credit to Professor Ananta Chandrakasan, who came up with this big idea in 1990, where he said, instead of having 1 core run at 4 gigahertz, what I can do is use lots of littler cores, not run them at 4 gigahertz, run them at 1 gigahertz, slower frequency, okay? You run them at slower frequency, but then still you find, okay, I've gone from 4 gig to 1 gig, but I'm using 4 cores. If I use 4 cores, I'm still back to whatever power that the 1 core had. But the key trick was when you lower the frequency on a core, you can also reduce the voltage. And the moment you reduce the voltage, your power goes down quadratically. That's the trick. So by lowering the frequency and having more cores and lowering the voltage, my power goes down quadratically while number of cores grows linearly. So by having more and more cores and lowering the frequency, I can actually get to be more and more power efficient. So we just have to do more of that. Have more cores, reduce the voltage, lower the frequency, and use newer processes and other tricks to reduce power. But I think power is one of the biggest challenges of our time. Yes?
The Aeronautical Development Agency, or ADA, of the Department of Defense R&D is the nodal agency for the design and development of the light combat aircraft.